Hi, thanks very much for inviting me. I'm going to tell you a little bit today about a system we built called the Bionimbus Protected Data Cloud that whose goal is to make it easier for researchers to get access to large amounts of cancer genomics data and to be able to analyze it in a safe and compliant fashion. Let's see. The talk has 4 points, 4 parts. I'm going to begin by just talking a little bit about the growing amount of cancer genomics data and some of the opportunities and it provides and some of the challenges. I'm going to talk a little bit about biomedical clouds in general. Then I'm going to talk about the system we built called the Bionimbus Protected Data Cloud. And then I'm going to talk about a new initiative which is creating biomedical data commons called the Biomedical Common Cloud. So this is a picture of the a sequencing facility at the Broad Institute of MIT and Harvard, and as you can see, it's factory size, and sequencing centers like these are producing larger and larger amounts of data as the cost of sequencing comes down. And sort of 2 facts to keep in mind as you just order of magnitude as you listen to this talk. If you think ahead for the next few years, sequencing is going to come down to roughly $1,000 over the next couple of years per whole genome, and continue to drop after that. The other thing to keep in mind is, for order of magnitude, if you sequence a tumor, a whole genome sequencing of a tumor and of the matching normal tissue, it's roughly a terabyte of data. So that will fit, sort of comfortably in a disk that you can just hold in your hand. But the interest, as we'll see, is to do larger and larger numbers of those as the price drops and as our ability to get useful information out of that data increases, and that's where the challenge is. So one of the projects that is providing lots of important data is called the Cancer Genome Atlas, or TCGA. It's a large-scale NIH-funded project that's collecting and sequencing both a disease and normal tissue from 500 or more patients across 20 different cancer types. So the target when this project is done is to have roughly 10,000 patients across 20 different cancer types. And in general, there'll be the sequence from a tumor and the matching normal, so that you can look for variation across both the tumors and the germ lines, and begin to understand how to improve the diagnosis and treatment and management of cancer from this data. Currently, there are about 6,000 patients available today. That's roughly 600 terabytes of data. It's going to grow to approximately 2.5 petabytes over the next couple of years. And at the beginning of the project, there was exome data, which is much smaller than whole genome data. And so some of the difference in sizes is the more recent data tends to be whole genome versus exome. Exome is the portion of the genome that codes protein. This is one of the papers, and there are quite a growing number of papers that have come from the Cancer Genome Atlas projects. This just shows you some of the reasons that data analysis and the scale of the analysis is so important. For this particular type of, here there are about 178 cases that were analyzed, both matching normal and tumor, but the number of mutations was, the mean of the number of mutations across these 178 cases in the exomes was 360. the mean of the number of copy number variations, CNV, was 323, and the mean of the number of rearrangements was 165. And so, this particular type of lung cancer is complex with, an average number of several hundred mutations, copy number variations, and rearrangements. And the goal, as we'll see, is to use this information to stratify the disease so that the strata are easier to understand and easier to treat and easier to diagnose. Making this much more challenging is that tumors are not static. They change over time. They change in response to the environment, say from treatment, and they are not spatially homogeneous. There'll be different clones, and the clones will have a different genomic structure. And so the temporal and spatial variation of the tumors is one of the things that's making the analysis of making the action and analysis of this data more complicated. Here's a particularly simple set of, this is from breast cancer. These are features, the tumors were analyzed from about a couple dozen patients. Various features were produced. A principal components analysis was done. And for this set of patients, there was a fairly simple clustering into two types, two strata, one which is estrogen receptor positive and one which is triple negative, and these are treated quite differently. The red, the estrogen receptor positive tumors respond to particular treatments where the triple negative doesn't. And in general, this is sort of the paradigm to sort of get genomic signatures to sort of in a precise way based on not on the way the tumor presents histologically, but in terms of the specific signatures genomically of the tumor to get to identify which treatments will work on which patients. So we have a problem fundamentally. We have a growing amount of data that's very, very rich. And on the left, each column is a particular patient. This is from the Cancer Genome Atlas, and this is the beginning of the. There are a number of papers that have been coming out that are trying to do an integrative analysis and understand the heterogeneity of tumors. The vertical axis is the position along the genome, and the horizontal axis are different patients, different tumors. And the idea is to sort of begin to cluster these in different ways. So we have a lot of data that's coming about. We have constant or shrinking amount of dollars, and this is creating the challenge that it's just not practical for every research group that wants to analyze this data to put up an infrastructure that in a safe and compliant fashion can can analyze and 2.5 petabytes of data, and even if we could, it probably wouldn't be a good use of our resources. So the community for the last few years has been trying to work out ways we can sort of tackle in an efficient way analyzing this amount of data. So we really do have a problem in that even to move 2.5 petabytes of data across the internet is a challenge, to manage is a challenge, to do it in a safe and compliant fashion is a challenge. And so there's really an informatics bottleneck that is A, making it hard for the community to move ahead, and B, sort of restricting access of the analysis of data to sort of the larger medical research centers and sequencing centers that have the resources and experience to tackle problems of this size. And that's just not ideal. So, as I said, setting up and operating the sort of data management, data analysis infrastructure at this scale is a problem. At the petabyte scale, that sort of would handle, say, 1,000 matched tumors. So again, you can hold the data for one tumor and match normal in your hand, but 1,000 of them is, requires a couple racks of computers, and most research centers can't provide that for all the researchers that need it. So one possible solution, in the same way that commons have emerged, from, where grazing could, there were community commons for grazing so that all the cattle in the community could graze, and as long as there was, some of them didn't sort of unduly sort of eat the grass, keeping it from the others, but with with some simple rules, commons are very effective ways to provide resources to community. And so the idea that's come up, that's sort of emerging by consensus over the last couple of years, is instead of which in the past with microarray data, which was quite small, every single researcher would have their own copy, do their own analysis, and write their own papers. With this large-scale genomics data from these projects with 1,000 or 10,000 patients, the idea is to create commons of biomedical data for the community. We need a way to manage those, and clouds are an effective way to provide, in a centralized way, access to data and compute for large numbers of people around the world. So if we were to build one or more if we were to create commons, manage them with clouds, and learn how we can interoperate these, this provides a sort of a go-forward solution for the community. And sometimes this is the shorthand way of summarizing this problem is, we may have a $1,000 genome, but the analysis of a genome costs closer to $100,000. And so we need a sort of a radically new way to do this. And this notion of building a number of data commons, using clouds to manage them, and interoperating them is one of the important approaches that's emerging. And so if we're going to, as we do this, there's sort of three questions to keep in mind, and that's sort of what I want to address in this presentation. The first question, what's the scale that's required for biomedical clouds? How do you design these clouds? And, how can different biomedical clouds interoperate? And I'm going to use the word biomedical for, a cloud that contains genomic data, electronic medical records, probably imaging data, of the full range of data that you would look at in the biological, the clinical, the translational component of trying to understand disease, its impact, its prevention, and its treatment. The challenge that has been motivating our group and a number of other groups out there is what you might call the million genomes challenge. So, sequencing 1 million genomes would probably give us the power to really change the way in a fundamental way how we understand genomic variation and its ability to do a more precise, genomically driven precision diagnosis and treatment. And again, the numbers are, there's nothing magic about 1 million, but it's sort of an interesting number in that, 1 million 1 terabyte data sets is 1,000 petabytes or an exabyte. So that's a good number that, that's a big challenge to be able to do data analysis at that scale. It would cost about 1,000 times 1 million or $1 billion. That, is a big number from one metric, but if you think of the cost of the, healthcare as $2.6+ trillion each year, spending $1 billion over a few years in a way that would has the potential to, dramatically improve the way we diagnose and treat disease is not a lot of money. And you could almost argue, we can't afford not to do projects at this scale in terms of the potential it has for improving diagnosis and treatment and management. So this is sort of a picture that has emerged in the community. We sort of do analysis at the scale. Currently we can sort of, as you'll see, do it at 10,000. If we can increase that by 2 orders of magnitude, we can do what's usually called precision diagnosis, that is, use genomic signatures to improve diagnosis. Precision treatment, use genomic signatures of the disease tissue to try to get to predict which protocols, which drugs will work on which tumors and which individuals, and then improve our understanding of the basic pathways and regulatory structure that sort of enable cancer to progress and give us the potential to manage it with the appropriate treatments. So I'm going to talk a little bit about the cloud infrastructure with that as an introduction, and then this will be a short introduction, and then we're going to dive in to the particular structure we've built and have been operating for the community for the last 6 months or so. The way I think of it is, we know if we want to look at distant objects, we can use a telescope, and if we want to look at small objects, we could use a microscope. And both of these instruments gave us, 1 to 2 orders of magnitude of power that wasn't available with the naked eye. So if we want to design a sort of a datascope that would allow us to work with 1 to 2 orders of magnitude of more data than an average research group could do today, what would that look like? And I think many of you may recognize this. This is one of the pictures of a Google data center that was released. And so the way I think of this is, a datascope is a sort of a custom data center that's designed to manage large amounts of scientific data for the research community. And that would easily give us, 1 to 2 orders of magnitude more power than most of us use today to look at data. What you need is software that scales to a data center that has the property that if I were to add a rack of infrastructure, I can analyze more data, but I don't have to change the software, I don't have to change the algorithms, I don't have to change anything, but I can scale by adding racks of equipment, quickly add the racks, get more power, but not change the software stack. We don't have software in bioinformatics that scales to data centers today. So that's sort of how we looked at this project. How do we do software and provide sort of algorithms that can scale to data centers? And you can just say, we have a solution to that. Why not just use Amazon? And there's certainly, no matter how we do this, when I say Amazon, I mean commercial providers of cloud services, whether it's Amazon, Rackspace, or many of the others out there. No matter what we do in the future, these kind of commercial cloud service providers are always going to be an important part, and we're going to always have to figure out how to interoperate. They provide scale. With a credit card, you can be up and operational very, very quickly, and they have a rich, wide variety of offerings. So given all the commercial cloud service providers, why, you can argue that there should be no reason for scientists to do this on their own. And, I think what we are trying to understand in this project and in other projects people are doing is, when do researchers just use commercial providers, and when do we build our own, and how do we interoperate these, and how do we interoperate with other, what are sometimes called community clouds or science clouds. And so one of the reasons is, at a certain scale, these clouds provide just lower cost. So, for example, we're running sort of on the order of magnitude to 20 to 30 rack cloud today for science researchers called the Open Science Data Cloud, and we'll typically send a bill out to one of our groups. We sort of, we're funded by foundations now and a little bit from the federal science agencies like NSF and NIH. But if we were to charge Amazon scale rates, what we would be asking our researchers to pay would be maybe for some of them $40,000 or $60,000 a month in terms of the resources they use, and that's just not in the budget of anyone. So, at a certain scale, community clouds are just much more cost efficient, or more cost efficient. You can also, which is important for what we're doing today, can build specialized, secure, compliant infrastructure, say to handle electronic medical records, human genomic data in a way that will work for a community. And over time, it's going to be easier and easier to interoperate with cloud service providers, but there's always going to be a trade-off where we could do very specialized type of infrastructure, and we're doing this for some of the particular projects we're doing right now that just aren't available or won't be available for some time in commercial providers. And the other reason, some of the projects that are sequencing data, cost hundreds of millions of dollars, and you might, the community, can just feel that it's just, this data is too important to put exclusively with a commercial provider, which may be out of the business in a few years. If this is data that has been provided with tax dollars, and it's really important to have a long-term home. And you might have it backed up in different places, but I think there's from a viewpoint of stewardness. How do you become a steward of this data, especially as it's done with taxpayer money? It's just too important to rely exclusively with a commercial cloud service provider. But that doesn't mean we won't be interoperating. And so on the next slide this is sort of a schematic of what a $200 million data center may look like. There'll be a customer-facing portal, accounting and building, monitoring, network security, forensics, automation of the provisioning of infrastructure, and a lot of hardware, but not that many people running it. And it's a scale that you measure in megawatts. So if you want a litmus test where someone really understands big data, if they talk in terms of terabytes and petabytes, they probably don't understand big data. If they talk in terms of megawatts and tens of megawatts, that's sort of a sign that they sort of do this for a living. And so the question is, can we build a scaled version of this for the scientific community, more specifically for the cancer genomics community? And so over the last few years, mainly with funding from the Moore Foundation, we built something called the Open Science Data Cloud, which is designed for researchers. Right now it's about 5 to 6 petabytes, but it's growing. It has a customer-facing portal. This is built over a combination of OpenStack and all open source software, including Eucalyptus, GlusterFS, Hadoop, etc. It has accounting and billing. It has some specialized software stacks and services. It has compliance and security so that we can work with human genomic data. It has the beginnings of an infrastructure automation so we could efficiently add racks. Right now we're operating about half a megawatt, so it's about 30x of the scale I just showed you with 5 to 6 engineers. We're trying to use mainly community software that will scale. So we use, again, as I mentioned, OpenStack, Hadoop, Gluster, but we did write a little bit of software, the minimum amount just to make this work, something called Tukey, which is the portal and the middleware, Yates, which is our infrastructure automation and management, and some open source software for the, for moving these petabytes of data and synchronizing petabytes of data. And, at a high level schematic, there's 3 types of data that a biomedical cloud is going to have. It's going to have the public data, and that includes the 1,000 genomes. This is open access data that anyone can look at, PubMed and literature, etc. It's going to have what is, controlled access data because of the consents required with the people who donated the data. This includes the Cancer Genome Atlas, a pediatric version of that called Target, and more generally data, including GWAS data that is in something called dbGaP, which is the NIH facility for controlled access data that's made available to the community. And in general, up to now, you can download that data, but you can't compute over it. And then there'll be electronic medical records and other type of data that contains enriched clinical data about the phenotypes and other kind of information that you need to analyze genomic and other data. I think the most important thing is that to be self-service so that you can launch this. A group can get up and operational with a cluster that's over the data. So there's a data commons, and you can analyze that data with a self-service infrastructure, and that you have sufficient scale that if I want another 100 cores, another 25 terabytes of data, it's just easy. And so I'm going to show you what we've done right now with something called the Bionimbus Protected Data Cloud, and this right now in here is the Cancer Genome Atlas, and we're working with the community to add additional data. Our goal is to get additional data in there, and just to sort of, in the jargon that people sometimes use, we want to democratize how we give people access to data and make it easy for researchers to quickly get the data they need so that they can analyze the cancer and other data in a safe and compliant fashion. So I'm going to turn this to Alison Heath, who's going to show you this in action.
Good afternoon, everyone. So this is going to be a live demo of our Bionimbus Protected Data Cloud, which is always kind of scary, but here we go. So anyone can go to bionimbus-pdc.opensciencedatacloud.org. If you are someone who has access to this protected data from TCGA, you would go to Apply, where you fill out a form, and we would actually be able to automatically add you. Once you have an account, you can go to the console to log in. And then this is some of the software we had to write, because NIH is the one who says whether you have access to this data or not. So we actually use a federated login system where you go and you hit the NIH servers so that we know that you have access to this data. So here we are at the NIH login. And this will forward your credentials back to us. We'll check that you have indeed access with TCGA. And once the credentials come through, you log in and you see kind of a quick summary. Since I've been doing some large-scale analysis, we've increased my quota quite a bit to pretty much be able to use the whole system. People have quotas so that we can share this in a commons manner. We increase that and decrease that based on different project needs. Some of you might be familiar kind of with this interface. As Bob was mentioning, we try to not write too much software and just write the parts we need. So this is based on OpenStack's Horizon project, but we've added quite a number of plugins such as authentication, as well as some other interesting query tools I'll show you in a moment. So here at the top, we have standard images that we distribute from our group, and at the bottom we have community images that people have made public. So you can launch your VMs here. Additionally, we have a new service called Launch Cluster. So this will automatically start up a cluster that's managed with a cluster management software called Torque. So you can instantly have a cluster ready that you can submit various analysis jobs to you using the specific instance, so the software that you're used to using is already there and ready for you. And then, of course, you can view your instances and see what you currently have running. In addition, we've been starting to work on better ways to actually manage the TCGA data. People who have actually used it might know that all the data is listed as these long random strings, UUIDs, that can be difficult to sort through. So what we've done here is we've created a query builder so people can have instant access to the different subsets of data that they want. At the top is where the data will actually arrive in your VM. You can type a query name. So for example, if I was interested in ovarian whole genome, you can do that. And then here are the various metadata terms that the Cancer Genome Atlas provides. So for example, disease abbreviation, we'd want OV for ovarian. The different library strategies, so RNA-seq, whole genome, whole exome. Here, if we're looking at whole genome. And then there's a variety of other different ones, like the sequencing centers, whether it's tumor normal, for example. And all of this data is already on the protected, on Bionimbus PDC. And as you can see, you know, each one of these analyses are actually pretty large, and they're in a compressed format, 300, 100 gigabytes. But here you can go through and see all the data that matched your query. And then you go and you would launch an instance. You'd create whichever image you want. So if you had an image you created with your analysis tools, they'll be already loaded there. We have to name our VM here. And then you can select what size you want. So we offer everything from 1 CPU to the largest offering right now has 16 CPUs with 65 gigs of memory. And what will happen here is all those data sets that you saw will get loaded up as symlinks into your VM. So you have instant access to your data in a folder along with all of your analysis tools already there. So this one actually takes a few minutes to load up, so I'm just going to show you real quick on one that we already have. Of course. For those of you who are used to using command line tools, we're using PuTTY here to SSH into the protected data cloud. We see our VMs here, and now I can just SSH or connect into my VM, and I put all those query results in /temp. You can put them anywhere you want on the VM. If we go into ovarian whole genome, you'll see there's a metadata folder that has a list of all the files that matched it in a manifest. So if you wanted to repeat this analysis or share with someone exactly what data you did this analysis over, you could just share them that file. And then in the data folder, you have all the various ovarian whole genomes that are available through TCGA. And if you look in these folders, these are BAM files, which is how TCGA right now is distributing the folders. So here what I've done is I've started up a server. It has the software that I'm already interested in with doing my analysis here, and my data is already there ready to go without having to download it, without having to set up any sort of infrastructure. So that was just a quick tour of it. I think I'll turn it back to Bob now.
So thank you, Allison. The standard tools that most of the projects that are currently using the Bionimbus Protected Data Cloud use, the bioinformaticians in the project would typically create an image with our help or on their own with all those tools, and then they could, for any image that they launch, whether it's a cluster of images, for every image they launch, whether it's a cluster or a single one, those tools would be available there. So I just want to walk through in a couple slides a sort of a summary of what Allison just showed you. This is human genomic data, and because of the consent process, the particular data from the Cancer Genome Atlas requires that you get consent from NIH to be able to, through their data access committees, to be able to use it. And so the first step always is to get access to the data. As the consent process, as there are newer consents that make it easier to look at data that are beginning to be deployed. But currently right now, the data like this is typically controlled by data access committee, and you apply to that to get access. Then what you would do at a standard research center is hire the people who know clusters, the people who know networking, the bioinformaticians to sort of set up an environment to handle 100-plus terabytes, whatever you need. You would need typically, because it's this data is usually you're supposed to treat it like PHI data, protected health information data. Typically, you would need to get permission from your research center that you set this up correctly. You would then set up your pipelines. This data is distributed from CG Hub, a data center out of San Diego today, and it can take days to weeks to get the data. Then you begin analysis. With the Protected Data Cloud, as Allison just showed you, you still need to get access to the data, but once you have that, you could do exactly what Allison just did. It took her 5 minutes, and 5 minutes later, if she had a pipeline and was she could begin analysis. So we've taken sort of and again, the point of clouds like this is to make it easy so that in literally a few minutes, as Allison just showed you, you could begin analysis of the data. Now, this data is complex, and understanding it is a challenge. That is not going to go away. So you still have to think hard about how you do the analysis, but what we can, with approaches like this, what the community is doing is just making it faster to get access to the data and to be able to begin a fruitful analysis. So right now, this is the only cloud-based computing system that interoperates with NIH in this way, so that we can track your credentials, use your logins, and really make it as easy possible to get access to this data. More and more systems, I think, like ours, will be approved to work in this way, because the point of what we're trying to do is sort of work with the community to put a critical mass of data in here. Right now, we're going to, in a week or so, we have about a half of the TCGA. We'll have the other half in a week or so, 1 to 2 weeks. We're trying to get a critical mass of data in a commons that makes it as easy as possible to make discoveries. We have the 1,000 genomes and other public data sets in the open access portion of Bionimbus. And we're also sort of building from a genomic to a biomedical cloud. We're doing pilots. We have about 10 pilots right now. There's a medical image pilot. There's a pilot with electronic medical records. All these things can be brought into this kind of environment in a secure and compliant fashion. So one of the main reasons Alice and I are giving talks about this is to sort of work a process to get a number of pilots using this, so that we can understand, how to build out systems like this at larger and larger scales, and how to begin to have a large enough infrastructure so that it makes sense to interoperate with other infrastructures like ours. So the simplest way, if you just want small amounts of resources, they're free. If you just want to compute over some of this data with some of the smaller, with a modest number of core hours and storage resources, just apply, and hopefully you can make a discovery. If you do make a discovery, we encourage you to mention us in the paper, but you could do whatever you want. But this assumes that you have access to the data, you have a dbGaP access, and your VRA Commons account, because that's the only way with the current contract we can make this data available to you. The next thing you could do is we have people using 80,000, 100,000 core hours and smaller number of core hours. If you're interested in a particular project, send us a note, and we have a small group of people that sort of do an allocation of resources, an allocation community, so we can sort of choose a number of pilots and give people large enough amounts of resources that they can do something non-trivial. We have people doing this on imaging, taking data from the Cancer Imaging Atlas and combining it with TCGA. We have people doing mutation, looking for fusion genes that are using a large number of resources. So through this allocation process. So the second thing is, do a one-page application and ask for resources. The third is, we sort of think of if you have a project, a funded project, you can sort of get a fairly large amount of resources, a rack at a time available. If you can get the funds, we'll work with you to purchase, set up, and operate racks of resources for you. That's sort of a colo, in the same way that the scientific community has sort of colo fiber. This is like colo clouds, so that you could do science at scale. And then, what we're very, very interested right now is, is working with people who can contribute interesting data sets, so that in the same way Alison showed you getting access to this 600 terabytes of Cancer Genome Atlas, and similarly we can get access to 1,000 genomes, et cetera, that you can contribute interesting data to the commons. So under this view, it used to be that the only people smiling were biologists or clinical researchers at the very largest centers that could set up infrastructure like this. We're trying in a modest way to have more researchers at more places smile like that person at the top, because as long as we can sort of work to get large amounts of data in, once the data is in, if it's public data, it's there. If it's community data, we can empower communities of researchers and collaborations. And if it's you can if it's data just for your group, you can try to interoperate in a secure way with us. So I want to end in the last 3 or 4 minutes coming back to the Protected Data Cloud has been up and operational, I think, since February or so. and we have a number of projects, pilots using it, and we're adding adding additional pilots as resources permit. And but the one thing we've done is I want to tell you about is looking at the current Bionimbus Protected Data Cloud is a facility at the University of Chicago that we make available to the community, and we're working hard to ask how do we interoperate and how do we scale this out. And so the Biomedical Commons Cloud is the next phase of that. And here is this notion is could the right not-for-profit federate these clouds in an interesting fashion so that we work across medical research centers to create a community of clouds in different ways. And so the Open Cloud Consortium, which was the driving force for the Open Science Data Cloud, just created something called the Biomedical Commons Cloud Working Group, where the OCCs involves companies, universities, national labs like NASA, Livermore, and through this contract with NIH, NIH is sort of beginning to work in the way I just described through the Biomedical Protected Data Cloud. What we're trying to put together with the Biomedical Commons Cloud in this working group, which has just launched, is the right software, which we've talked a little bit about. We're in the process of getting a 5-year sort of portion of a data center for this project. We're working to put the right data in. We just described what we did with the TCGA. We have a process to bring authorized users access to the data. We have a lot of compliance and security. We try to bring the people together, and we have a sustainability model. And so that project, which will be an expansion across multiple sites, we have about 10 organizations. Across multiple organizations, we have about 10 organizations currently involved in planning for the Biomedical Commons Cloud, medical research centers, cancer centers, universities. And so, the key questions, what are the common services? How do we get a critical mass of data? What's the governance structure? What's the sustainability model? And where we are right now is sort of at the, order of magnitude 10 petabyte scale, 10,000 patients. And, the million genome challenge is, how do we, over the next couple of years, work together as a community to sort of expand this kind of infrastructure out 2 orders of magnitude to hopefully get a critical mass of data that can change the way we do precision diagnosis and treatment of cancer. And so we have some time for questions. Let's see here. I'm going to see if I can see some questions. Okay, so let me start with the first question. Oops, give me just 1 second. Let me read that question. Thank you. So the first question is, I'm a newbie to the world of cloud computing and medical research. Is there a way for me to learn about this kind of stuff? Well, it depends. There's a couple different things to learn about. One is certainly cancer genomics. One is how do you get access to the type of cancer genomics data that is in TCGA. Another question is, how do you, if you're interested, how you begin to work on creating this kind of infrastructure. And the last, probably the most interesting question, now that this infrastructure exists, how do you make the, what are, it's a wide open industry in some sense, in that this amount of data with this power of computing has really not been available before, and so it's just an absolutely interesting, it's an absolutely great time. It's a great time to be able to sort of begin to do analysis like this. And so, each of those questions has a slightly different answer. I think what I'll do is there's no immediate answer. I mean, there's no one-sentence answer to any of those questions, but I'll, if you Google biomedical clouds or TCGA or some of the technologies I mentioned, you can learn a little bit about it. I'll probably put some references out there if you want to dive in to do this in more detail. Let me go to the next question. This is, does NIH approve of using controlled protected TCGA data in Amazon or other clouds? First of all, I haven't learned very much in my life, but the one thing I've learned is never to comment on other organizations. So if you want NIH's current policy on whether you could use public clouds like Amazon or other private clouds, this is the question, does NIH approve of using controlled protected TCGA data on Amazon or other clouds? I think you need to talk to your NIH program manager or the relevant person at NIH or dbGaP to understand, where they are on this. It's, something they're constantly evaluating, but I'm going to flip that to NIH because they're the experts. So the next question, Allison's demo, she launched an image with, sorry, I just lost the focus of that, of the screen. I got the screen back. In Alice's demo, she launched an image, 20 gigabytes root. How did she get the TCGA data? How did the TCGA data get mounted? I think the question is, was it copied or was it symlinked?
Yeah. So in the /temp that was symlinked, what I didn't show is there's also a full mount of the TCGA data, which is on the remote Gluster file system in /GlusterFS. So just temp was a symbolic link to the larger mount in a /cluster.
Let's see here. I'm just trying to see if I can. All right. I was just trying to get more screen space to read this. With all the data analysis now at hand, how do you suggest we are all speaking the same language to advance research faster? That's a good question. In other words, there's a couple ways we can interpret that question. One is there's a lot of research being done as what is the right way to get statistically meaningful results out of data this size, and what is the right way to structure the analysis. What is the right way to sort of put the data on a common footing because it comes from different sequencing centers, different machines, et cetera. That's an ongoing discussion that all the analysis working groups from the different projects are doing. There's a lack of interoperability of some of the basic tools. Sometimes the result of most groups is a little bit of contributed data and occasionally contributed software, but not data in a way that could be sort of there for other people to analyze it as is. And so one of the things I would hope would come from projects like this is to make it a little easier with some of the software technology that is available in a common cloud, in a biomedical data commons, to sort of lower the impedance to have other people use the data you produce, because the data can be left in the cloud. It could be also, a copy can be left in the cloud, and you can make it easy for other people to compute over that, perhaps by leaving your virtual machines and others for other people to sort of your images available so other people could create virtual machines from them. Next question, is this open source infrastructure approach useful for tackling rare diseases? Yes, I think it is. We're working, I mentioned 10 pilot projects, and we're working, some of those are, we currently are not working with any specific rare diseases, but that we're in discussion, and I think it would be useful, but I think the same approach would work. We're just not working with any of those currently, but are wide open to it, as I think other groups like ours would be. Next question, we're a medical device manufacturer. Can your service host our big data applications privately as an infrastructure as a service? So what I didn't talk was about the ecosystem we're trying to create. We're trying to create a very, very rich ecosystem because everything we do is open source. Our interest is in facilitating medical research that's data intensive at scale. So we are actively beginning to build out an ecosystem. So even though everything we do is open source, we understand that a lot of the interesting technology there is done by companies that will be part of a larger ecosystem. So yes, we're actively trying to build out this kind of ecosystem at scale around big data biology. Next question. Allison's demo, she launched an image. Was I going the wrong direction? Let me try to refresh this again. I think I answered all the questions. Do we have any other questions? I may have dropped one or two.
Thank you, Bob. Let's take a peek here. Folks, we are at Q&A. If you do have a question for Bob and Allison for what they've been talking to you about in the live demo they've showed you, please send it in now while they're with us. Just open your group chat widget, type it and send it in, and they'll answer it while we have them with us. And Bob, as we give it just one moment here to see if anyone has additional questions, folks, we would like to let you all know that Bob is going to be speaking live at O'Reilly's Strata RX conference next month in Boston, September 25 through the 27th. We push out a link to you all so you can view his session, the details, and get more information on the event. Allison is going to be along with him as well. They're going to do a workshop to really deep dive into that demo, and you can meet him, meet Allison, and ask lots of good questions there. So we hope you're available to join us at that event. And let's see here. I'm not seeing any additional...
Can I make one final comment?
Yes.
So, I don't often do this, but I'm going to encourage anyone who's listening to we're an all-volunteer organization. Everything we do is open source, and we're trying to create large-scale commons of data to make it easier for the medical researcher. So, at lunch today, what I encourage you to do is to just think about this for a few minutes, turn in stop working on your normal job and volunteer to work with us because you'll have a lot more fun. So that's the last thing I'd like people to think about.
Excellent. And with that, folks, we're going to say a very big thank you to Dr. Grossman and to Allison for their outstanding presentation today and for sharing all their knowledge and expertise with us. Thank you both so much. Folks that attended our event, we thank you for attending, and we hope you benefited from it. And Bob, I just want to let you know, I'm looking through the chat here as the audience is talking, and boy, oh boy, they're letting us know that they're giving applause in the background and that they thank you for the exciting work, and lots of people really enjoyed the event. So great. Thank you, folks that attended. We thank you for your time, and we hope to see you at our next event. And for those of you that are able to attend the Strata conference in Boston, it is September 25 through the 27th. This will conclude our event today. Thank you, everybody. Goodbye.
Yaz, are you there?